Okay, so hello everyone. The title of my thesis seminar is Semantic Symmetry in Transducers. And Shaull Almagor is my master's advisor, of course. Okay, so before we begin, I thought it would be nice to talk about the journey of mine in the academia. When the first degree was nearing its end, I was thrilled, of course, but I was not well satisfied with what I learned. I mean, yes, it was an entire degree we're talking about. Of course, I learned an awful lot. But still, something was missing. And it was that I never had to come up with new solutions on my own. I mean, clearly we had to think and find solutions to algorithms and data structures, but it was less inventing and more discovering. I also had the opportunity to work in the high-tech industry during the first degree. The problems we faced there were definitely more original and challenging. And yet, because of that, the industry is business-driven and running from deadline to deadline, it lacked an entire spectrum of problems that I had not yet touched. And so I decided to continue to masters. I would just like to note that I'll be taking a break from the pure academia as I join a research team in IBM in July, where my team and I will work on hybrid clouds. And the tools and knowledge that I gained from the masters will surely be beneficial. I'm also humbled to have my future manager and my future team leader as well here listening to my thesis seminar. I'm grateful for that. So my master's journey began just alongside the COVID pandemic's first emergence in Israel, March 2020. I remember I was yet to finish a project or two from the first degree. So for a while, I had a foot in each degree, except that my actual feet were, in bed. I'm kidding. So anyway, I began looking for the right field of study. And what a relief was it in the first semester that it was already obvious to me. It was the course on automata, logic, and games that filled my cup. I had enjoyed studying this course so much that I knew this was what I wanted to work on for the duration of my master's. And so we met, the lecturer of the course, who is Shaull, and I. And in my opinion, there was immediate chemistry. We both love mathematics and theoretical computer science. We are both musicians. We both kept a grave distance from the moda of the age, that is machine learning, of course. That was a joke. And we both love it when proofs require no more than a pen and a paper. So we talked and formed a research goal. And when he suggested the initial idea, he handed me a research paper he'd just finished working on process symmetry in the probabilistic setting. And that was the beginning of the journey. Now, reading research papers and generally learning about previous work was such an enjoyable activity. You could see the excitement of the authors in their findings and the amusing methods of proof that they used. And if you want a real taste of the fun in research, just check Shaull's YouTube channel. Of course, reading is nothing like making my own hands dirty, so to speak, with research. So trying out things myself, seeing ideas build and crumble, that was the journey. It's the suspiciously colored berry in a basket of berries. You don't know if it will taste good or bad. Anyway, so in the research, we focused on what is called formal verification. In a time of rapid developments in both software and hardware systems, it had become ever more essential to check against malfunctions or misbehavior in a system to guarantee both quality and security. And if you want to check the behavior of a system in all its possible configurations and states, that would be a lot to check. So attempting to study systems without doing a full exploration is the general motivation for formal verification. And so in this seminar, I will present a notion of symmetry in systems called round symmetry, which could be exploited to facilitate the verification of properties in a system. We will generalize this notion of symmetry in such a way that we turn to study the relation between systems that we call round simulation. Without further ado, let's begin the seminar with a story. So say we have a robot, a father robot. We also have 3 feeding platforms, a feeding hand, and 3 child robots, gray, red, and yellow. Now, in every time step, each of these child robots could ask for food. And having only one feeding hand, father robot will have to decide whom to feed in every time step. And so we have a scheduling problem. So let's say father robot decides to use the round-robin scheduling algorithm, which means that in the first time step, he only considers the robot on platform 1 if he's asking for food. In the second time step, he considers the robot on platform 2. In the third, platform 3. And in the fourth, we go back to platform 1, and so on. And so, for example, if in the first time step, the robots gray and red ask for food, and in the second and third time steps, robot yellow asks for food, then the input would be the number of platforms, the number of the platforms asking for food. So it would be 1, 2, then 3, and then 3. So that would be the input to round robin. And the output, again, is what father robot will be able to feed. So since he will be able to feed robot on platform 1 in the first time step and the robot on platform 3 in the third time step, the output of round robin would be 1 empty 3. Great. Now, let's say that on some very cloudy day, such as today's, the robots decide to switch places. So the robot on platform 1 goes according to this permutation to platform 2. The robot on platform 2 goes to 3, and 3 goes to 1. So now if we had the same order of requests, the input would be permuted to be changed to 2, 3, and 1, and 1. And the output in this case, well, father robot will not be able to feed anyone. And so the input would be empty, 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 which is unfortunate. It's unfortunate because, well, on the one hand, of course, that's how round robin works on these kinds of inputs. So that's expected. But on the other hand, round robin feels very much symmetric. After all, it does consider each of these robots in every round of its running. And this permutation is analogous to real-world processes switching ports to a system. So since it feels symmetric, this means that it exhibits some kind of symmetry that we wish to capture and put into words, and hopefully we could see this symmetry also exhibited in other systems as well. So that would be our objective, to capture the symmetry of round-robin and similar systems. Enter symmetry by rounds. Well, it's by rounds because, as I said, round-robin works in rounds. It reads and it works with its input in a round by round by round fashion.
Wheels on the bus go round and round.
Thank you, nursery rhymes. So anyway, and therefore we will look at the input word for round robin as a concatenation of rounds, each round of length 3, of length k in general, and here k is equal to 3, which is the number of platforms. Great, so now let's move back to our story and see how this symmetry unfolds. So we have this input and the original output, 1 empty 3, and we also had the permuted input. Now notice the following. There is a way to shuffle this permuted input, and by shuffling I mean the reordering of letters, such that this shuffled input, the output on it, which is 1, 2, empty, is itself a shuffle of 2 empty 1, which is the permutation of the original output. This sounded confusing, I know, but I'll say it again and trust me that it's intuitive. We have the initial input and the permuted input. Round robin satisfies the following property. There is a way to shuffle the permuted input so that the output on the shuffle is itself a shuffle of the permuted output. Let's see this along with a table. So we had some input x in rounds. Now the output on x, let's call it y. So y is the output of round robin on x. Now we have permuted x. Okay, so now some basic or naive kind of symmetry would say that, well, the output should also be permuted in the same manner. But we have seen that this does not hold in round robin. So we cannot say that the output is pi of y. So pi of y is like outside of this table. However, what we can say is the following. There is a way to shuffle this pi of x into some x prime so that the output on x prime, which we call y prime, is itself a shuffle of pi of y. So in order to reach from pi of x to pi of y, we had to do some shuffling in between. And that would be the notion of symmetry by rounds, or what we call round symmetry. We will put it into words in a bit. For now, let's again understand the difference between permutation and shuffle. Because we do these two kinds of transformation on the inputs. So let's assume we have some input x and some round inside this input, which is that round that we have seen. Think of the permutation as an up-down transformation of the input. So for example, the number 1 here, according to the permutation, it has to move to 2. So it's as if we move 1 into 2, right? And likewise, we could move 2 into 3 and 3 into 1. That would be the permuted input. Shuffling, however, is when we take these three, all the characters inside the round, we shuffle them and put them in another order. So that would be the shuffled input. So we could see that these two transformations, since shuffling is like a left-right transformation, are independent. They do not interfere. So if I took the same input and first shuffled and just then did I permute, I would get the same output. And moreover, shuffling is done in a per round fashion, so we cannot shuffle between the rounds. And it's also commutative, so that this x prime is also, the permuted input pi of x is itself a shuffle of x prime. Cool. Now, we had all this in order to reach the formalism. So now, to begin the formalism, we first talk about our model, which is the transducer. For those of you who know automata, well, it's like an automaton with an inputs and outputs. For those who don't, well, it's a standard formalism for modeling reactive systems, so systems with input and output. So here we have the transducer for round robin for 3 processes. And let's see this, let's build it together. If we begin at the initial state, recall that in round robin, we first consider the first platform. So we look at the first letter and we ask if platform number 1 exists in this letter or not. So if number 1 is in the letter, well, great, we output 1. We can feed the robot number 1. Here we have the outputs in red. If not, well, then we output nothing, empty set. Likewise, we do for the second step with platform number 2. If it exists in the second letter, we output 2. If not, we feed no one. And so on for 3, and then back again to 1. So now that we have this transducer of round robin in mind, we are now ready to define round symmetry. So we say that a transducer T is called K-round symmetric if for every input x and a permutation pi, there is a way to shuffle this permuted x so that the output on the shuffle is itself a shuffle of the permuted original output, which is exactly what we had earlier. We can shuffle the permuted input and get a correctly shuffled permuted output. Notice also that this kind of symmetry is semantic in the way that it did not consider the structure of the model, the structure, of the system, rather the behavior of the system. And so it's semantic. Moreover, notice that we have permuted both the input and the output. So let's consider a transducer that's identical to T, except that it permutes wherever gets in and wherever gets out. Let's call this T pi. And given such a transducer, we can now rewrite this property of round symmetry by saying that we wish for every input x to have a shuffle of x such that T pi on the shuffle is a shuffle of T of x. And so now instead of talking about a property of the transducer, we could now turn to talk about a relation between two transducers, which leads us to round simulation. So we say that a transducer T2 K round simulates transducer T1, and we denote this with the less than sign, if for every input x in rounds of k, there's a shuffle of x such that T1 on x is a shuffle of T2 on the shuffled x. So first of all, setting T2 to be the T pi of earlier basically gives us round symmetry. So this shows that round symmetry is a special case of round simulation. Now, just to see this a little bit better with the drawing, say we have T1 round simulated by T2. This means that for any input x for T1, along with its output y, there's a way to shuffle this x so as the output on it in T2 is itself a shuffle of y. So that's the kind of simulation that we have in round simulation. Great. Now, as we have seen, round simulation is a generalization of round symmetry. So now we turn to study round simulation. And in fact, it's what we are going to aim at for most of this seminar. And for round simulation, there are two main decision problems that we consider. There's the fixed round simulation and existential round simulation. In the fixed case, we are given two transducers, T1, T2, and also the round length K. And we ask if T1 is K round simulated by T2. In the existential case, we are given the two transducers, and we ask if there exists a round length K for which round simulation holds. So the first problem is more suitable for cases like round robin, where we know the supposed round length of symmetry. The second is when we intuitively feel that some system is symmetric, but we are not sure with which round length. Great, so now let's move on to study these problems and their solutions. And we begin, of course, with the easy case, so as to say. So that's the fixed round simulation. And for that, we begin to define a tool. The tool is the shuffle closure non-deterministic finite automaton. Okay, so we denote this with shuff k of t because it's obtained from the transducer t given round length k. And it goes like this. Every sequence of k transitions in the original transducer gives one transition in the shuffle closure, but it's a transition that's oblivious to the order of letters. I'll say it again, this time with the example. Say we have round length equal 2, and this transducer. Now we say every sequence of 2 k equals 2 transitions, such as this transition of AB outputting 0, 1, every such sequence gives one transition in the shuffle closure automaton. And it's a transition between the same two states, so between S and T. So here we have this transition of AB, 0, 1. And moreover, it's a transition that's oblivious to the order of letters. So we could think of this transition as actually 4 transitions with all the shuffles of AB, along with all the shuffles of 0, 1. And and so notice that here the letters in the shuffle closure are actually pairs of 2 words, each of length k. One word corresponding for the input and the other corresponding to the output. And what this construction gives, is the property of shuffle invariance, which means that for every state S and a pair xy of length k words, so a letter in the shuffle closure, if we also have a shuffle of x and a shuffle of y, then this shuffled letter, x prime, y prime, behaves identically to the unshuffled letter xy. So basically, all the shuffles behave identically. And since this is true for the characters, it's also true for words over this shuffle closure automaton. So that would be the shuffle invariance. That it is the automaton is invariant under shuffles. In order to construct this automaton, we have used an intermediate automaton called the trace DFA, which basically takes out the output from the states into the transitions entering the states. So the outputs are here on the transitions. And so if we had a toolbox, the toolbox would contain both the trace DFA and also the shuffle closure itself. And now, like taking this toolbox along with us, we reach this lemma, which is the main lemma for deciding fixed ground simulation. It says that for given transducers, T1, T2, and ground length K, round simulation holds between T1 and T2 if and only if there is containment between the languages of the shuffle closure automata for T1 and T2. I'll try to explain why this is the case intuitively. Well, because if we get some input for T1, which is X, along with its output Y, well, this containment means that there's some shuffle of the input, X prime, so that its output in T2 is going to be itself a shuffle of the original Y, which is basically round simulation. Now, what we have done here is reducing the problem to the containment problem of NFAs. And so a direct corollary is that the problem is in p-space. Moreover, we have also shown p-space hardness of the problem, even for simple cases like k equals 2, by a reduction from the universality problem of NFAs. And so a corollary is that the problem is p-space complete with regard to its complexity. Great, and now we are ready for the, well, maybe harder but more fun case, which is the case of the existential round simulation. I remind you that now we ask if there exists a round length K for which round simulation holds. And so we find an upper bound on the minimal round length for which round simulation holds. That would be our plan. That is, we want to effectively compute some upper bound K0 such that if round simulation holds between these two transducers, then it also holds for some round length that's less than this upper bound K0. And now, notice that once we have this upper bound, it means that it is enough for us to check for round simulation for round lengths up to this K0. So basically, we have some finite upper bound that we have to check only up to. And so the problem renders to be decidable. Great, so finding this K0 would be our goal. And here too, in order to do that, we use tools. So the first tool is going to be the type of letters. So in any transducer or automaton, the type of a letter is the transition matrix that it induces, which means the following. Let's look at this transducer here and consider the letter A. We have 3 transitions with A. And so the transition matrix for the letter A, or the type of A, is going to have 1 in 3 places, in 3 entries. So it's a Boolean matrix. It's going to have 1 in the entries that correspond to these transitions, and there's 0 in all the other cases. For example, this one here corresponds to the transition from Q3 to Q4. We could do the same thing for the letter B. Great, okay, so now we know what types are, but in fact we are more interested in types of the shuffle closure automaton. So let's build the shuffle closure automaton for T for round length 2, which starts as we had earlier with the AB01. So that's AB01. There's also the BB below, and so on. So believe me, that's the shuffle closure. And now here too, we could talk about types of letters. But now remember that the letters here are actually, well, they are oblivious to the shuffles inside them. And so, in fact, it's as if we have lifted this definition of types to this shuffle closure kind of letters. All right, so here too, we can talk about the types of the letters. So if we consider the letter AB01, here too, it has 3 transitions. And so That would be the type of the letter. And now we could talk about not the type of one letter, but the set of all the types and of all the letters in this automaton. So that would be the type profile. It's the set of all types of all letters. And in fact, it's a set along with the multiple. No, never mind. Yeah, it's like the type set. It's all the types of letters that exist in this shuffle automaton, shuffle closure. And so in this case, we have 3 letters, and so 3 matrices. Now, bear in mind this last matrix, the topmost. It has 2 ones here and all the rest 0. Just bear it in mind because now we're going to move to talk about round length 3, k equal 3. And when we build this automaton and consider its types, we will notice that there's some letter with the same type as earlier. Well, it's not surprising because, well, the types, which are Boolean matrices, there's only a finite amount of them. Yeah, there's a finite number of states, so there's a finite number of types. And this also means that there's a finite number of sets of types, which are type profiles, up to the multiplicities of letters, because some letters might have the same types as other letters. But now let's consider the sequence of automata. As we have started to do, we considered the shuffle closure with k equals 2 and 3. Let's now consider all the shuffle closures with an incrementing round length. And, well, we said that there's finitely many type profiles up to this multiplicities of types when letters have the same types. We now further claim that if we consider that sequence of automata, there is some round length k0, after which no new type profiles appear. Which means that when we consider this sequence of automata, when we reach k0, we will have already seen all the type profiles that we're going to see. Now, we will soon see why this claim is important, but I would just like to state that we tried to tackle this claim and to prove it in many, many ways. It was very challenging to us. Like we tried using a software program, like a coding to do that, to help us understand. And we tried many other things, and I could swear I saw some Jordan matrices on my whiteboard at some point. And in the end, we could prove it using logic, which was very exciting to understand that. So we could actually prove it using what's called the Pressburger arithmetic. So we have defined a formula, theta t of k, which states the following. It states that the type profile of the shuffle closure with round length k is exactly some t. So here t is a type profile. And now, well, that's good because research on Pressburger arithmetic has shown us that satisfiability could be effectively determined for the Pressburger arithmetic formulas. And we can also find a witness kt. So this witness kt basically is a round length that has this type profile t. Great. So now just taking the maximum of all of these witnesses will grant us the k0 that we wanted, the k0 after which no new type profiles appear. Why? Well, because we have taken the maximum of all the round lengths for all the different type profiles. We have considered for each type profile some round length that has it. And so this k0 would be a round length after which no new type profiles appear. So in terms of tools, well, here we had the tools of types, type profiles, and the Pressburger arithmetic. And along with these tools, just as earlier, we arrived to the main lemma for this point. And this lemma also tells us why this k0 was important. It says that if type profiles for shuffle closure with round length k and k prime are equal, yeah, so if the type profiles for round length k and k prime are equal, and if this is the case for both transducers, for both T1 and T2, then the containment problem, the containment of the languages of the shuffle closures with round length k holds if and only if it holds for round length k prime. Now, I remind you that this containment, we have seen it earlier in the fixed round simulation. So basically, we're saying that the problem of fixed round simulation for round length k and k prime coincides when their type profiles are equal. And so since k0 of earlier has told us that any round length after it will have some type profile that we have already seen, well, this means that we don't have to check the bigger round lengths. It's enough to check only up to this k0, which would be the upper bound that we were looking for. Now, there's a small caveat here, which is that here we are talking about T1 and T2, so two transducers which could have a different state space, so different states. And so there's need for some synchronization. And this synchronization of the type profiles, in order for them to be equal, is achieved by taking the product automata of the shuffle closure. So basically, we could take the shuffle closure, the product automata of them, once with the accepting states of that of T1 and once with that of T2. We will call these B1 and B2. And of course, they depend on the round length K. We call this product automata redundant, well, because it seems as though we're tracking the same thing twice. For example, well, in B2, we don't need the states of T1, but we keep them nonetheless in order to have the same state space, and so the same type profiles. Great. Now, we will not get much into the proof, but the proof structure of this lemma is interesting. So I would like to state it here. So here we have a diagram of the proof structure, and notice the following. Since we know that type profiles are equal for the world of K and the world of K prime, then we could map, using this mapping phi, we could map each letter in the world of K prime, for example, to a letter with identical type in the world of K. So basically, we could map every letter in this shuffle closure to a letter with identical type in that shuffle closure. And so, knowing that we can do that along with phi, if we now assume some containment, because we want to prove equivalence. So if we assume the left side and want to prove the right side, now, well, if we take some word in this shuffle closure, and of course, we now use B1 instead of the shuffle closure. So if we know that some word is a word in B1, by applying this phi on all its letters, we arrive to some word that has the same types. And not only that, it's a word in the world of K. And so this containment that we assumed tells us that this same word also exists in B2 with round length K. And so applying back this reverse phi, because it holds in both cases, we would reach the word W, and we would have reached that this same W exists both in B1 and in B2. And so we have shown that this containment holds whenever that containment holds. That was, of course, very roughly speaking. I hope this was this gives a feeling for how these type profiles and their equivalence works. Great. So in terms of tools, here we have used the redundant product automata. And now in the last part of the seminar, I thought we could talk about feasibility a bit, because, well, complexity, well, I mean, it's not fair to say it like this, but if we calculate very roughly the complexity of what we have done now, it could reach 5 exponential, which means that, well, the time needed is like an exponent to an exponent and an exponent 5 times. But that's not really fair to say that, because we haven't really gotten into the intricate details of the constructions. So, for example, the Pressburger arithmetic formula, maybe we could maybe we could do the satisfiability in a way that's more efficient to how we did it, to how we calculated it. So that's the first thing in terms of complexity. On the other hand, we do have a lower bound. We do have an exponential lower bound for the minimal round length. So I thought it would be interesting to see that because, well, as we saw earlier, we have used tools from other fields for some proofs of ours. Here too, we will use a tool from number theory. We will talk about primes here. So that was exciting as well when we arrived to this conclusion that this will help us here. So the example goes like this. Say we have this transducer T1, which only accepts inputs of the form 1, 2, 3, 1, 2, 3, and so on. And it outputs just as well, 1, 2, and 3. And so for any input x, the input would have the form 1, 2, 3 to the power of t, and the output would be the same. Great. Now, if we will now, in a bit, talk about T2, but for now, for any T2, in order for T2 to round simulate this T1, I think it's very natural and it's very intuitive to ask that the round length would be divisible by 3. So that's because there's this inherent symmetry in T1 in rounds of 3. So it makes sense that the round length for the simulation would also be divisible by 3. Of course, this needs proof, but it's doable. And now, if we turn to talk about T2, notice how it works. Here we have some initial state, and this initial state can read either 1, 2, or 3. And also, these 1, 2, or 3 actually correspond to some prime numbers, which are the first 3 prime numbers. So consider P1, P2, and P3 to be 2, 3, and 5. And now, the transducer behaves like this. Every time it sees 1, it does not only read 1 letter, it reads P1 letters, which is 2 letters. And it outputs twice the number 1. So here we have the first letter is 1, the second letter no matter what, and we output 1 in both cases. And then we're back to the initial state, behaves like the initial state. If it sees 2, likewise, it reads P2 letters instead of just 2, and it outputs the number 2 3 times. And if it sees 3, it reads P3 letters, and it outputs the number 3 5 times. Now, okay, it doesn't matter now to understand the intricate details of that, but you can see that there's this pattern of primes, and what this gives is the following. If, well, now we want to go and talk about round simulation, and we consider some word for T1, which is 1, 2, 3 to the power of k divided by 3, because we're considering now just one round of length k. And, well, we are looking for some shuffle of that x prime and some shuffle of the output, like some shuffle of x prime whose output, y prime, is itself a shuffle of the original. But, and here's the catch, in order for this output to be, in order for the output of x prime to be a shuffle of that, the number of 1s and 2s and 3s will have to be k in the output. But in order for the number of 1s to be k in the output, now the number of 1s must be even. And so k must be divisible by 2. And likewise, for example, 3, in order to have k times the number 3, this k must be divisible by 5. And so all in all, this k, which is so this k must be divisible by all of these primes that we are considering, 2, 3, and 5. And since they are primes, it also must be divisible by the product of these primes as well. And, well, so we have seen that the round length for simulation must be exponential in the sum, must be in the order of the product of the primes. And it is known from number theory that the product of the primes is exponential in the sum of the primes, which is also the same order as the number of states in these transducers, because here we just have the number of states, which is in the order of the sum of the primes. So yeah, this gives us the lower bound. Now, there's another addition to feasibility, and in fact, it's something that requires future work. It's an open problem for us, which is the mapping between rounds. If we consider some round, some T1, which is round simulated by T2, and if we consider some round for T1, well, of course, we know that there's some shuffle of this round that works in T2, which means that its output in T2 is also a shuffle of T1. So we could think of this mapping between the round and the correct shuffle as, well, as a mapping. We will call it psi. However, if we now take some word that has many rounds, it is not necessarily the case that the round in, for example, round R3 has to be shuffled in the same manner no matter where it is in the word. It's not necessarily the case. Sometimes a round has to be shuffled in different ways according to where it is in the word. So it's like saying that it's not true to say that the psi of W, of the whole W, is equal to the concatenation of all the psis of the rounds. And therefore, now the question is asked, if we look at some general word W with some n rounds, is there a way to describe this mapping? Is there a way to calculate this psi of W with some model that's sub-Turing? Well, because of course we can write some algorithm that just tries all the shuffles of the word. So that would be that wouldn't be much. So we ask ourselves if there's some model, some computational model that could do that for us, which is sub-Turing. And yeah, that's an open problem, as I have said. There is something that's known for us, which is that look-ahead based models do not work, which means even like if we now have some round in our hands, even if we know some couple of rounds ahead, some finite number of rounds ahead, this would still not help us decide how to shuffle this round. So we need to read the whole word. And this same way of thinking also can show that this model cannot be regular. Yeah, so I guess that now we have reached the conclusion. So we have defined round symmetry, which is a kind of semantic symmetry, as we have seen. It considers the behavior of the system. We have also defined round simulation and shown that it's p-space for the fixed round length and decidable for the existential. For the future work, of course, there's this problem of the effective description of the mapping to shuffled rounds. And we think that models like streaming string transducers and bimachines might help, for those of you who might know them. And one can also consider other notions of symmetry and stability for transducers. So in round symmetry itself, one could consider the shuffling not letters, but rather the signals inside the letters, for example. Maybe that would be interesting in itself. And one could also consider other settings, such as the infinite words and the probabilistic setting. For example, some kind of symmetry that only holds asymptotically. So that's all for the seminar. Thank you for listening. And if you have any questions or anything to say, please go ahead.